We are going to discuss an important property of Fourier and Laplace transforms called convolution. Let me first recall to you the definition of the Fourier transform. So the Fourier transform of a function written f of f is the integral, or sometimes called g of alpha, is the integral from negative infinity to infinity of the function as a variable t e to the minus I alpha t dt. So you're integrating out the variable t, and the variable alpha is left over, and that function of alpha is called g. So the Fourier transform is a function g of alpha. The Laplace transform is defined similarly. The Laplace transform of any function f, which is given in terms of the variable t, is another function g of alpha, which is given by the integral from 0 to infinity f of t e to the minus alpha t dt. So these are the two objects which I introduced in previous videos. Convolution describes the process by which you multiply transforms. You cannot just multiply transforms like that. For example, if you have two Fourier transforms or two Laplace transforms, how do you multiply them? So for the Fourier transform, the multiplication is called the convolution operation. So let me just take the g. I'll suppress the argument alpha for now. I'll just take gi equals the Fourier transform of fi, which means that I can write this for I equals 1 or 2, just to have a pair of them. So one of the first things that you need to know is that there's a definition of the inverse transform. The inverse transform fi is just the inverse of gi. So that's applying the inverse operator. That's called the inverse transform. So the inverse transform of gi gives you back fi. Similarly for Laplace transforms, I won't write that. So for the Fourier transform, if you have two functions f1 and f2, the convolution of those two things of the functions f1 and f2 is defined like this. So you take f1 and f2 and put this asterisk in between them, and that is the integral from minus infinity to infinity f1 with argument x minus u and f2 with argument u du. So the final result will be a function of x, because you're integrating out the variable u. And this can be shown very easily to be the same as f2 convolution f1, because all you're doing is making a change of variable of x minus u equals u prime. Okay, so the convolution operator is symmetric. It doesn't respect the order in which the functions are convoluted. Now, why is this convolution even important? By the way, for the Laplace transform, you have a similar definition. So this is for the Fourier transform, the convolution operator for a Fourier transform. And for a Laplace transform, it's going to be the following: f1, f2 of x is going to be the integral from 0 to t. So that's going to be a function of t. G of t minus tau, f1 of t minus tau times f2 of tau d tau. And this is the same as f2 convoluted with f1 as a function of t. So both of them have very similar structures. Of course, the Laplace transform itself is defined only from 0 to infinity, and that's reflected in the definition of its convolution operator. So that's the reason why the convolution for the Laplace case goes only from 0 to t rather than from negative infinity to positive infinity. There are other reasons, but they are a little too involved to be mentioned here. So I have the definition for the convolution of two functions. Think of it as just a definition. People made up a way of multiplying two functions with a star in between them to be this thing here. So what is it really? It is you're taking the product of those two functions, but they are not products at the same value. This is at x minus u and that's at u. So they're offset a little bit. The variable x is kept fixed, but the u variable is allowed to change. This one inherits the u variable at every step. This one takes the difference of x and u. So it's like going over a rectangle of width x minus u and height u, and then you're going all over the u plane for a fixed value of x. So think of it like that. It's a special kind of multiplication or averaging. Now the reason the convolution operator is even invented in the first place is because of two important theorems, and these are known as the convolution theorems. So the first theorem is that the Fourier transform or Laplace transform of a convolution is the product, is a regular product. So just multiplying the two things is a regular product of the Fourier transforms or the Laplace transforms. So let's try to write this in symbolic form. So if I have functions f1 and f2 and I symbolically write it like this, Fourier transform of f1 convolution f2 is going to be the Fourier transform of f1 times the Fourier transform of f2. That's the beautiful result that you have, known as theorem 1. The proof of these results does not concern us, and we'll relegate them to either the notes or the book by Boas. The second theorem is the converse of this theorem, and that is the converse of this theorem is going to be, if I have f1, f2, then that's going to be the Fourier transform of the inverse transforms, convolution of the inverse transforms. So that's going to be f inverse of so here's what I'm going to do. Rather than write it like that, sorry, this is going to be f of, not the inverse, it's just the Fourier transform of those, the transforms of those functions. So I should not have written the inverse thing there. So that's going to be f of f1 convoluted with f of f2. So that's like the converse of the previous one. If I want to just get the product of the two functions, what do? I take the Fourier transform of the Fourier transforms of those functions convoluted with each other. So these are the two important theorems. Now convolution operators are extremely useful because of some other properties that they have. We've already seen one property of convolution, and that is if I have f1 convoluted with f2, that's the same as f2 convoluted with f1. And by the way, all these theorems that I stated here for the Fourier transform are also true if you replace the Fourier transform f with the Laplace transform L. The theorems remain valid. So you don't necessarily have to have f there. You can also put the L. And these theorems, especially when we study Laplace transforms, will play a very big role in finding out things like shifting lemmas. So the property of this we've already seen. Then there's a distributive property. If you take the function f and two other functions f2 and f3, then that's going to be f1 distributed with f2 plus convolution with f2 plus f1 convolution with f3. And this property is very important, and it's called the associative property. And later on in this week's videos, I will talk about the Dirac delta function. For now, you just accept this, please. The next property is called the existence of an identity element. So if I have a delta function, the convolution of f with delta is the same as the convolution of delta with f, and that's going to be equal to f. So that's called an identity element. Those who know a little bit of group theory will start seeing some interesting structure develop here. The convolution, in a sense, is a group-like structure, and of course the inverse is already there because of this theorem. So we can think of the convolution as a group-like object. So I'm just going to let you think about that, and just want to mention one word of caution. The identity is not 1. So some people may think the identity is just the function 1, but you can show that f convoluted with 1 is not equal to f. So 1 is not the identity. Instead, we need to invent a special kind of function, or a special class of functions called the Dirac delta functions, which will be dealt with in a later video of this week. So these are the definitions of convolution of a Fourier and a Laplace transform. The convolution of all other kinds of transforms also exist, but we won't examine them in this course.